Hi guys, today we are going to look at ninth standard first chapter mathematics. Okay, that is number systems. Okay, let's see the introduction part. In your earlier classes, you have learnt about the number line and how to represent various types of numbers on it. Okay, like this. All right. Okay. Just imagine you start from zero and go on walking along this number line in the positive direction this way. Towards your right is positive from 0, towards your left is negative. As far as your eyes can see, there are numbers, numbers and numbers. Now suppose you start walking along the number line and collecting some of the numbers, get a bag or ready to store them. You might begin with picking up only natural numbers like 1, 2, 3 and so on. Then this collection becomes natural number collection. You know that this list goes on forever. Yes. Why is this true? There are infinitely many numbers of natural numbers. That's why it is true. So now your bag contains infinitely many natural numbers, right? Recall that we denote this collection by the symbol n, right? This is the symbol n. Now turn and walk all the way back. Pick up 0 and put it into the bag. Now you have the collection of whole numbers which is denoted by the symbol W, right? 0 plus natural numbers is nothing but whole numbers, okay, or denoted by W. Now stretching in front of you are many negative integers. Put all the negative integers into your bag. What is your new collection? Recall that it is the collection of all integers, okay. It is denoted by the symbol Z, okay. Integers is denoted by Z. All positive negative, negative integers, okay, plus whole numbers. Why Z? Z becomes from the German word zahlen, which means to count, okay. Are there some numbers still left on the line? Of course there are numbers like 1 by 2, 3 by 4, or even minus 2005 by 2006. If you put all such numbers also into the bag, it will now be the collection of rational numbers, okay. This collection, it is denoted by q, right? The collection of rational numbers is denoted by q. Rational comes from the word ratio and q comes from the word quotient, okay. You may recall the definition of rational number. A number r is defined as a rational number if it can be written in the form p by q, where p and q are integers and q not equal to 0. Why do we insist that q not equal to 0? If q becomes 0, that number becomes undefined. Okay, right. Notice that all the numbers now in the back can be written in the form of p by q, where p and q are integers, q not equal to 0. For example, minus 25 can be written as minus 25 by 1. Therefore, the rational numbers also include the natural numbers, whole numbers and integers, right? You also know that the rational numbers do not have a unique representation in the form p by q. For example, 1 by 2 equal to 2 by 4 equal to 10 by 20 equal to 25 by 50. This one is multiplied with 2. This is with 5. 5 no 10. This is with 25. Okay. 47 by 94 and so on. These are the equivalent rational numbers or fractions. However, when we say that p by q is a rational number, then we represent p by q on a number line, okay. We assume that q not equal to 0 and that p and q have no common factors other than 1, that is p and q are co-prime, okay. So on the number line, among the infinitely many fractions equal to 1 by 2, we will choose 1 by 2 represent all of them. Now let us solve some examples about the different types of numbers which you have studied in earlier classes. Are the following statements are true or false? Give the reasons for your answer. Every whole number is a natural number. Natural number? No. 0 is not a natural number. Every integer is a rational number? No. Yes, yes, right. Every integer can be rational number. Vice versa is not true. Every rational number is integer? No. That is what I told. Vice versa is not true. Alright. Find 5 rational numbers between 1 and 2. How to find? By averaging method. Okay. 1 plus 2 by 2 is nothing but find 5 rational numbers. 5 rational numbers he told. Okay. Then you must divide it by 6. Okay. 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6, and 6 by 6. 1 plus 2, 3 divided by 6. Mhm. Recall to find the rational numbers between r and s. You can add r and s divided by the sum 2. That is r plus s by 2. That is 3 by 2. Is number between 1 and 2. Now you can proceed in this manner to find more rational numbers between 1 and 2. Okay, that means between 1 and 3 by 2. Again, take the average. Okay, the other option is to find the 5 rational numbers in one step. Since we want 5 numbers, we write 1 2 as rational numbers with denominator 6. Right, this is what I want to convey. 6 by 6 or 12 by 6. So 7 by 6, 8 by 6, 9 by 6, 10 by 6, 11 by 6 are all the 5 rational numbers. That is easy method. Okay. Notice that in example 2, you are asked to find 5 rational numbers between 1 and 2. If you must have realized in fact there are infinitely many rational numbers between 1 and 2. In general, there are infinitely many rational numbers between any two given rational numbers. Let us take a look at the number line again. Have you picked all the numbers? Not yet. The fact is that there are infinitely many more numbers left on the number line. There are gaps in between the places of the numbers you picked up, and not just one or two, but infinitely many. The amazing thing is that there are infinitely many numbers lying between any two of these gaps too. So we are left with the following questions. What are the numbers? What are the left on the number line called? How do we recognize them? That is, how do we distinguish them from the rationals or rational numbers? These questions will be answered in the next section. Let's now look at exercise 1.1. Is 0 a rational number? Yeah, 0 can be expressed as 0 by 1, 0 by 2, 0 by 4, 0 by minus 1, like that. So that is a rational number. Okay. Find 6 rational numbers between 3 and 4. Which method you want to go? You want to use the second method, right? Then you what you have to do is 6. They asked 6 rational numbers. So 6 plus 1 must be your denominator. 7 must be your denominator. 3 can be expressed with 7 denominator. Is it possible? Mm-hmm. Right. 21 by 7. Yes. 21 by 7 is 3. What about 4? 28 by 7 is 4. Then 22 by 7, 23 by 7, 24 by 7, 25 by 7, 26 by 7, 27 by 7 are those 6 rational numbers between 3 and 4. So 4. Okay. Find 5 rational numbers between 3 by 5 and 4 by 5. Which method you want to use? The second method. Then your denominator must be 5 rational numbers, right? Uh-huh. Right. 5 means 6. Denominator must be 6. So multiply with 6 on both numerator and denominator. 6 3 is 18. 6 5 is 30. 18 by 30. 24 by 30. Okay. So 19 by 30, 20 by 30, 21 by 30, 22 by 30, 24. Hmm. Is it giving me more than 5? Let's check once again. Let's write that number first. 6, right? 3 by 5, 4 by 5 is 1 by 5. Okay, take 1 by 5 common then. Okay, 3, let's say these are 3 and 4. So 6 multiply with 6, 18 by 6, 3, 24 by 6. So 19 by 6. Okay, 20 by 6, 21 by 6, 19 by 6, 20 by 6, 21 by 6, 22 by 6, 23 by 6 are the 6 numbers. Now you can easily multiply it with 5. Okay, that is the easiest way. We take 1 by 5 common outside. Okay, fine, right. State whether the following statements are true or false. Give reasons for your answer. Every natural number is a whole number. Yes, every natural number is a whole number. Natural number is a subset of whole numbers. Simply you can say. Every integer is a whole number. Every integer is also a whole number. No, no, not at all. Why? Negative integers are there. Every rational number is a whole number. Every rational number. No, no, no. Every whole number can be a rational number, but not vice versa. Okay, which can be written in 2 by p by q form. That is, let's take an example of 2 by 3. That is not a whole number. Okay, let's now look at irrational numbers. We saw in previous section that there are numbers on the number line that are not rationals. In this section we are going to investigate those numbers. Okay, so far all the numbers we have come across are of the form p by q, where p and q are integers, q not equal to 0. So you may ask, are there numbers which are not in this form? There are indeed such numbers. Okay, Pythagoras, the Pythagoreans in Greece, followers of the famous mathematician and philosopher Pythagoras, were the first to discover the numbers which were not rationals around 400 BC. The numbers are called irrational numbers. Irrational simply because they cannot be written in the form of a ratio of integers. There are many myths surrounding the discovery of irrational numbers by the Pythagorean Hipparchus of Croton. Okay, in all the myths, Hipparchus has an unfortunate end, either the discovering that root 2 is irrational or for disclosing the secret about root 2 to people outside the secret Pythagorean sect. Okay, outside the secret Pythagorean sect. Let us not go into those myths. Let us formally define these numbers. A number S is called irrational if it cannot be written in the form p by q, where p and q are integers. Okay, and q not equal to 0. You already know that there are infinitely many rationals. Turns out that there are infinitely many irrational numbers too. Some examples are root 2, root 3, root 15, pi, 0.10110, 410, like that. Recall that when we use the symbol root, we assume that it is the positive square root of the numbers. So root 4 is 2, though both 2 and minus root 2 are square roots of 4. Okay. Some of the irrational numbers listed above are familiar to you. For example, you have already come across many of the square roots listed above and the number pi. The Pythagoreans proved that root 2 is irrational. Later, in approximately 425 BC, Theodorus of Cyrene showed that root 3, root 5, root 6, root 7, root 10, root 11, root 12, root 13, root 14, root 15, and root 17 are irrational. Proofs of irrationality of root 2, root 3, root 5 shall be discussed in class 10. As to pi, it was known to various cultures for thousands of years. It was proved to be irrational by Lambert and Legendre only in the late 1700s. In the next section, we will discuss why and pi are irrationals. Okay, why these two numbers are irrationals. Let us return to the question raised by the end of the previous section. Remember the bag of rational numbers. If we now put all irrational numbers into the bag, will there be any number left on the number line? No. The answer is simply no. It turns out that the collection of all rational numbers and irrational numbers together make up what we call the collection of real numbers, denoted by R. Therefore, a real number is either rational or irrational, and they fall into only two categories. So we can say that every real number is represented by a unique point on the number line, right? Also, every point on the number line corresponds to a unique real number, right? This is why we call the number line the real number line. Okay, in the sorry for that. In the 1870s, two German mathematicians, Cantor and Dedekind, showed that the corresponding to every real number there is a point on the number line, and corresponding to every point on the number line there exists a unique real number. Okay. Let us see how we can locate some of the irrational numbers on the number line. Locate root 2 on the number line. How to locate? What you have to do is again, sorry for that. What you have to do is take a square of 1 centimeter side, not size, side, okay, and locate that on the number line. Place it on a number line with one side on the number line itself, okay. Then this side is 1, this side is 1. What about the diagonal? According to Pythagoras theorem, this diagonal OB equal to root over adjacent side square plus opposite side square, root over 1 square plus 1 square, that is root 2. That is what you want to look at, right? So take a compass and uh, measure this length OB and project this into P. Okay, just draw a line segment, okay, extending from B to P. So this length OP is nothing but root 2. Okay, using a compass with center O and radius OB. Okay, we drew an arc along the on the number line. Okay, locate root 3 on the number line. Once you got root 2, what you have to do again, extend BD such that 1 centimeter, okay, such that it will be parallel to OB, sorry, perpendicular to OB. Draw a line BD perpendicular to OB with a length 1 centimeter. Then this OD is nothing but root 3 according to Pythagoras theorem. So take a compass and measure this OD, okay, and draw an arc which intersects the number line at Q. So OQ is now root 3. In this way, you can, if you want to locate root n for any positive integer n after root n minus 1 has been located, you can locate root n after root n minus 1 has been located. Okay. State whether the following statements are true or false just by your answer. Every rational number, irrational number is a real number. That is correct. Every point on the number line is of the form root m, where m is a natural number. No. Yes. Not no. Every point on the number line is of the form root m. Every real number is a irrational number. No, that is also incorrect. Are the square root of all positive integers irrational? No. If not, given an example of the square root of a number that is a rational number. Root 4. Okay, that is 2, that is a rational number. So that root 5 can be represented on a number line. Yeah, that you can do by taking 2 and 1. Okay, 2 centimeter and drawing one perpendicular to draw a perpendicular of 1 centimeter from 2 centimeter. Okay. Classroom activity, constructing square root spiral. The large sheet of paper and construct a square root of spiral in the following fashion. Start with a point O on a O and draw a line segment OP. First draw OP1 of unit length. Draw a line segment P1 P2 perpendicular to OP1 of unit length. Now draw a line segment P1 P2. Sorry, P2 P3 perpendicular to OP2. Okay. Then draw a line segment P3 4 sorry, P3 P4 perpendicular to OP3. Continuing in this manner, you can get the line segment Pn minus 1 Pn by drawing a line segment of unit length perpendicular to OPn minus 1. In this manner, you will have created to the points P2, P3, Pn are joined with them to create a beautiful spiral depicting root 2, root 3, root 4, and so on. Real numbers and their decimal expansions. Okay. In this section, we are going to study irrational numbers from a different point of view. We will look at decimal expansion of real number and see if we can use the expansions to distinguish between rational and irrational. So we will also explain how to visualize the representation of real number on the number line using their decimal expansion. Since the rationals are more familiar to us, let us start with them. Let us take three examples: 10 by 3, 7 by 8, 1 by 7. Pay special attention to the remainder and see if you can find any pattern. And if you do this continuous division method, you will get this 3.333, here a 0.875. This is 142,857, again 142,857. Okay, these two are what to say, the decimal expansion is endless for 3 and 7 as the remainders. Okay, but the digits are recurring uh, decimals. Okay, but what about 8? This ended with only three digits, 3 or 4 digits, whatever it may be, how many digits, that doesn't matter, but that is a terminating decimal. Okay, these two non-terminating but recurring. So remainder is always 1. Here remainder 640. Here the remainders are repeating. Okay, what have you noticed? You should have noticed at least three things. The remainder say either become 0 after a certain stage or start repeating themselves. The number of entries in the repeating string of remainders is less than the divisor. Okay, in 10 by 3 it is always less than 3. 1 by 7 there are only 6 entries. Alright, 3, 2, 6, 4, 5, 1 in the repeating string of remainder 7 is the divisor. Okay, if the remainder repeat, then we get a repeating block of digits in the quotient. For 10 by 3, 3 repeats in the quotient, and 1 by 7 we get repeating block of 142,857 in the quotient. Although we have noticed this pattern using only the examples above, it is true for all rationals of the form p by q where q is not equal to 0. On division of p by q, two main things happen: either the remainder becomes 0 or never becomes 0, and we get repeating string of remainders. Let us look at each case separately. The remainder becomes 0. For example, 7 by 8, we found that the remainder becomes 0 after some steps and the decimal expansion is 0.875. For example, 1 by 2, 0.5, 639 by 250, 2.556. In all the three cases, the decimal expansion terminates or ends after a finite number of steps. We call the decimal expansion of such numbers terminating. Okay. Second case, the remainder never becomes 0. In example 10 by 3 and by 7, we notice that the remainder repeat after a certain stage, forcing the decimal expansion to go on forever and forever. In other words, we have a repeating block of digits in the quotient. We say that this expansion is non-terminating. Okay, non-terminating, recurring. Okay, or repeating. The usual way of showing that 3 repeats in the quotient, so put a bar, 3.3 bar. Similarly, here 142,857 is repeating, put a bar on top of it, where the bar above digits indicates the block of digits that repeats. Okay, right. So all these examples give us here different example: 3.572, 72. 72 is repeating, put a bar on 72. All the examples gives us a non-terminating recurring decimal expansion. Thus, we see that the decimal expansion of rational number have only two choices: either they are terminating or non-terminating recurring. Now, suppose on the other hand, on your walk on the number line, you come across a number like 3.142678 whose decimal expansion is terminating, or a number like 1.2727, that is 1.27 bar, whose decimal expansion is non-terminating recurring, can you conclude that it is a rational number? Yes, the answer is yes. Okay, only two forms are there for rational number. We will not prove it, but illustrate this fact with few examples. The terminating cases are easy. Yes, we can simply put zeros. So how many decimal points are there? You put those many zeros on the denominator. You will get a number in p by q form. Okay, right. What about this? 0.3 bar. How to prove that this is how can you express this in p by q form? Simple. Only one digit is repeating, so multiply it with 10. This becomes 3.333. So the decimal point, the decimal expansion is equal in both the cases. So subtract this from this. 9x equal to 3, x equal to 1 by 3. Okay, got the point? So that can be expressed in the p by q form. Simple. Here two digits are repeating, so multiply it with 100. 100x equal to this. X you already know. Okay, then this guy separated 126 plus 1.27. This way also you can do. So 99x equal to 126, x equal to 126 by 99. Okay, when you have common factor, you can divide by that common factor and express it in co-prime form. Okay, where 14 and 11 are co-primes, so that this can be expressed in the p by q form. Yes, similar example. Okay, let us summarize our results in the following form. The decimal expansion of a rational number is either terminating or non-terminating recurring. Okay, moreover, a number whose decimal expansion is terminating or non-terminating recurring is rational. So now we know what the decimal expansion of a rational number can be. What about the decimal expansion of irrational number? Because the property above, we can conclude that their decimal expansions are non-terminating, non-recurring. Okay, so the property for irrational numbers, similar to the property stated above for rational numbers, is the decimal expansion of irrational number is non-terminating, non-recurring. Moreover, a number whose decimal expansion is non-terminating, non-recurring is irrational. We can come across an important uh, conclusion, right? Okay, recall this number from the previous section. Notice that it is non-terminating, non-recurring. Therefore, from the property above, it is irrational. Moreover, notice you can generate infinitely many irrational numbers similar to S. What about the famous irrational root 2 and pi? Here are the decimal expansion. They are non-terminating and non-recurring. This is 22 by 7 is not approximate value of pi. Sorry, is an approximate value of pi. This is not exactly equal to pi. Over the years, mathematicians have developed various techniques to produce more and more digits in the decimal expansion of irrational numbers. For example, you might have learned to find digits in the decimal expansion of root 2 by division method. Interestingly, in the Sulabha Sutras, Rules of God, a mathematical treatise of the Vedic period. Okay, treatise means a written work dealing formally and systematically with a subject. Period 800 to 500, you find an approximation of root 2 as follows: 1 plus 1 by 3 plus 1 by 4 into 1 by 3 minus 1 by 34 into 1 by 4 into 1 by 3. Notice that it is same as one given above, 1.14213, 14141, sorry, 414213, 414215. Same as the one given above for the first 5 decimal places, 41421. Okay, 41421, that is correct. The history of the hunt for digits in the decimal expansion of pi is very interesting. The Greek genius Archimedes was the first to compute digits in the decimal expansion of pi. He showed 3.140845 to 3.142857. Aryabhatta, the great Indian mathematician and astronomer, found the value of pi correct to 4 decimal places 1416 1416 using high speed computers and advanced algorithm. Pi has been computed to over 1.24 trillion decimal places. Okay, right. Now let us see how to obtain irrational numbers. Find an irrational number between 1 by 2 and 2 by 7. How to find? You can write decimal form and you can guess one number like this. Okay, let's see from exercise 1.3 in the next class. See how beautiful this nature is. You also start planting the trees. Let us bring a new change in our society. Let us plant the trees and let others plant the trees. Let's take this pledge seriously from now. Thank you.